introduction. So hi everyone, my name is Nikhil Barthwal. I work for Jet.com. I'll tell you briefly what Jet.com is. I'm going to talk about implementing event-driven microservices architecture in a functional language. We actually implemented it in a language called F#. For those of you who are not familiar, it's a language on .NET. And it has been a very positive experience. Obviously, choosing an unusual language has its own challenge. So I'm going to talk about I'm sure other speakers have covered this topic, but I'll just briefly talk about what event-driven microservices architecture is for those of you who don't know. And then I'm going to talk about the challenges and the benefits we had when we implemented it in F#. So let's actually get started here. So I'll start by a background of what Jet.com is. The company started in April 2014, but it was launched to public in July 2015, and we were acquired by Walmart in September 2016. We were one of the fastest growing companies in the world to reach $1 billion in valuation and the biggest exits in e-commerce ever to happen. And I have some numbers here. We have 8 million customers, 25,000 orders, 15 million. The crux of it is a dynamic pricing engine that saves you money as you shop. And the characteristic of this engine is that it does about 2 million calculations per second. So I have these numbers here. And the reason why I have these numbers is I want to give an idea of the scale at which we operate. So, when you operate at that scale, you have unique challenges. And it ties down to how using F# or a functional language in general helped us achieve that scale. So I'll start by the technology stack. We run on Microsoft Azure. It was a little bit of a business decision, right? At that time, Google Cloud Platform was not that mature enough for production. And you don't want to build an Amazon competitor on AWS. So Azure was the obvious choice. And Azure supports .NET Framework the best. So we decided to implement in .NET Framework. So we have a mix of technology. We have Kafka as our message broker. We have Redis. We have Splunk, New Relic for monitoring. Whole lot of things here. But the most controversial and unusual choice that we had was we decided to implement everything in F#. Actually, we decided everything first to implement in C# to give you the history. And then we re-implemented in F#. And then we found that F# implementation was much better. It gives us much agility. It was faster time to market. Overall, it was just much more positive experience in F#. So we scrapped the C# code. We re-implemented everything in F#, and we have been sticking with F# ever since. We now have about 250 engineers, actually, primarily. The company itself is obviously, if you include the Walmart, is the Fortune 1 company, but even without the Walmart part, it's about 1,000 people now. All right, so architecture. So we use domain-driven design to architect services. Again, I'll just give I'll cover each one of them in details later on, but to give you a very high-level overview, domain-driven design is a methodology that connects the implementation of a system to an evolving model. And then we have the event-driven architecture. Event-driven architecture, this is actually something pretty common, is that system is a reactive system that reacts to the event, right? So a very naive example of event-driven architecture is what happens when you go to an airport, right? So on Mike, they announce, you have a flight XYZ leaving the city in about 15 minutes. That's an event. And everybody in that airport, the passengers, they listen to that event. Some chose to react. Some chose not to react. Those who are boarding that flight would probably rush towards the gate and so on. But the key characteristic of event-driven architecture is that it's an asynchronous mode of communication where the sender has no knowledge of the receiver. It's actually passing through an intermediate broker. In this particular example, that broker is just air. Essentially, it's transmitting your sound, but generally how it works. Event sourcing is an architecture pattern where you store the state of your event as a series of deltas or series of changes. Event sourcing is actually pretty common. If you use version control system, Git, SVN, whatever, that's event sourcing. Because your source code, which can be considered as the state of your system, internally is stored as series of deltas or the commits. So you can just do a git log and you get all the commits, and then you can rewind back at one particular point of time. That's event sourcing. Another common example of event sourcing is banking, right? You have an account in whatever bank you have, and you do series of transactions, and your state of the system, which is the amount of money you have, your total balance, is essentially a sum of all the transactions, positive or negative. That's event sourcing, right? And then, of course, microservices is a very common thing. I mean, there have been a lot of speakers before me. So we have a microservice-based architecture. So let's actually go into details of each one of them. So now, domain-driven design. In domain-driven design, you have something called ubiquitous language, right? So ubiquitous language is basically a language that connects the domain experts to the developers. So when think of it as some kind of mini DSL, right? This topic itself, domain-driven design, obviously is a very big. You have wonderful books like Domain-Driven Design by Eric Evans, written 2003, and so on. So ubiquitous language is how the domain experts would communicate to the developers. Then you have a concept of a bounded context. I think there was a talk just before me that talked about bounded context, but generally, for a very complicated system, it's hard to have one model that represents the whole system. So what you instead have is you have these series of submodels that connect together rather than having one big model. And each one of these submodels is what you call as bounded context, right? So, so you would have a model, for example, for the sales team, for the developers, for the executives, and so on. And there's a common relationship between them, and they all together represent your system. So that's bounded context. Aggregates here means basically set of domain objects that can be treated together. For example, in an e-commerce world, you have a shopping cart. Now, when you think about shopping cart, it has one user, right, which has username, user details, address. It has line items. So I've purchased 3 of item X, 3 or 4 of item Y, and so on. And together, they constitute a shopping cart. But when we deal with the shopping cart, we deal with shopping cart as a whole. So that's an aggregate. So that's an example of bounded context, right? From a technology perspective, you have these bounded contexts, and they are then connected using various streams or queues and so on. Very common pattern in domain-driven design is CQRS, Command Query Responsibility Segregation. What Command Query CQRS says is that a service should be segregated into a read and write. So a read does not change the state of the system. Read is just a query. And then you have a write. Write would obviously change the state of the system, but the characteristic is read will always return you something, won't change the system state, whereas write is essentially a command. It doesn't return you anything. It might return a pass or a fail, the command succeeded, but it won't return an object. The common pattern of you have a function, you pass some argument to get something back, and there are some intermediate state change, variable change. CQRS prevents that. So CQRS obviously makes your system a little more complicated, but it has this huge advantage that now you have the read and write separate. So you can scale the read and write separately. What happens often is for most of the system, people have a lot of reads, but writes. 98% of the time you're actually querying something. Only 2% of the time you're changing. So there, in those circumstances, you can scale read much more than you can scale write. So CQRS allows you that segregation. Moving to the architecture layer. So essentially, domain-driven design, the common pattern is you have more 4 layers. There are actually different architecture models. There's an onion architecture. there's a hexagon architecture because it accounts into most of the test, basically additional hooks for you to test your system. But the most common and simple architecture pattern is that your application has 4 different layers. We start with the user design, user interface, which is often on the client side browser. You have your application layer, which is essentially where you do the transaction. You have domain layer. Domain layer is where the bulk of your code is going to be. So this contains the domain objects. And then you have the infrastructure or the persistence. So all your reads and writes to the database, your storage would go in the infrastructure. In a typical DDD pattern, the bulk of your code actually is in the domain layer. And as per the standard recommended practice, in domain layer, your objects are immutable. And this actually falls right into the strength of a typical functional language like F#, because I don't know how many people here are familiar with functional programming, actually, in general. Okay, that's good. Then I don't have to go into details of that. So in functional programming, most of the objects are actually immutable. And particularly, they can be modeled using what is called as algebraic data types. F# calls it discriminated union. For those of you coming from Scala, it's called case classes. I mean, these are different names, but essentially what they are is, we'll see some examples of these algebraic data types that can represent this domain model very effectively. And both Scala and F#, what it does is it lets you attach member functions to those types. So you can actually perform some calculation and return something else. There's a pattern in domain-driven design called anemic domain models, which actually is something that is an anti-pattern you should not be having in your code. And by attaching member functions, so anemic domain models is basically a model where your functions are nothing but getters and setters. So it looks like an actual function, but it's really nothing but a getter and setter. You want to avoid that pattern. So you can do that in F# pretty easily. So let's move to event-driven architecture. So here are some of the characteristics of event-driven architectures. You have these events, right? So event occurs when a change in the system happens. For example, let's say a common example is Facebook, right? Some event happened. You go to a place, you get married, you post a photograph, that's an event. So events happen, and and the listeners get notified. I'll actually stick back to my original example of airport I think that's very easy. So an event happens, an announcement happens that, hey, you're boarding your flight in about 20 minutes. That's an event. And all the listeners, in this case passengers, they get notified and some take action. But the key defining characteristic of this is that it's an asynchronous communication where the source does not know who the consumers or the listeners are. That's the key characteristic, right? So source just emits the event and that's it. Whosoever wants to do something will just do it. Source doesn't know, source doesn't care. And what it does is it's a very highly distributed, loosely coupled application. So you can add and subtract these producers and consumers. For example, think of Kafka, right? You have the message broker and you can add and subtract your producers and consumers. The consumers would not know if a new producer is added or vice versa. So let's move to event sourcing. Event sourcing, I briefly mentioned, it's basically where you store the state of the system as series of deltas, right? And what happens is that you can roll back in particular time in history. For example, banking, right? I can go back and say, 2 years from now, what was my bank balance? And what happens is when the event occurs, it triggers, and the listeners event triggers a state change. But the very particular characteristic of event sourcing is that different applications can process different same event and create a different view. One example I would give is Facebook, for example. An event happens and you have 3 different applications. You have your timeline, you have your info section, and you have your photo. So you post a photo, the same event on the timeline, it gets interpreted and it's post a photograph. Great. The info section gets that event, ignores it. The photo app gets the event, adds a photo to you, right? So the same event by 3 different applications gets interpreted in 3 different ways. Similarly, you get married. The info section gets updated. Your status goes from single to married. Your timeline updates, but your photo doesn't do anything. Okay. Microservices. So microservices are essentially small autonomous services that work together. They follow what is called as a single responsibility principle. And single responsibility principle states that your service should have one and only one reason to change. So they are basically small, focused, specialized things, specialized services, rather than having one big monolithic structure. And that takes me to the next slide, microservices architecture. So microservices architecture is essentially where you have these microservices working together. So you have this assembly of microservices, and your application might contain, we have about 1,000 services in production. So each one of those microservices runs its own process. Most of the people, what they would tend to do is they would have each microservice is in a Docker or a container of its own. It has its own memory, so it doesn't really conflict with other services. And it communicates with lightweight mechanisms. More often, it's often an HTTP protocol or something like a language agnostic protocol through which it communicates. So what are the advantages of microservices? Well, to start with, you have independent releasability and independent scaling. So let's say you have 2 teams. If you have one service, and if I deploy that service, other people's code also gets deployed because there is only one service. Whereas in microservices, typically, let's say you have like 50 teams, each team owns about 5 or 6 services. When I deploy my services, my change gets deployed, but it doesn't affect other people. So that way it allows team to move at their own pace. There's also better scaling, because let's say that there are parts of my system that gets overloaded, right? So I need to scale up. In a monolithic world, when you scale up the entire service. So you're scaling up parts that are underutilized, but you still need to scale, because when you scale everything. Whereas in a microservice, you can only scale the parts that are actually heavily utilized, and you don't have to worry about the ones that are underutilized. So it gives you a better utilization of your resources. You also have a technology heterogeneity. In a monolithic world, whatever language you choose, Java, C++, C#, your entire service uses that. Whereas in a microservice, you could choose, okay, I have 1,000 services, for 20 of them, Go makes the best choice. For 50 of them, Java makes the best choice. For 200 of them, C++. Each team can choose its own set of technologies. You're not actually tied to the global default. So that's one big advantage. You also have resilience. So if some of the services fail, the remaining would still work, right? Whereas in a monolithic, if there's an exception in the service at one part, the entire service goes down. And last but not the least, ease of migration. The reality is that the technology stack gets rewritten every couple of years. When you use a monolithic, it's all or none. In the sense, if you have to rewrite everything, or you don't rewrite. Whereas in microservice, what happens is when you rewrite, you can actually rewrite parts of it. This is a very interesting example from Facebook. So when Facebook started, Zuckerberg wrote it in PHP, and PHP didn't scale very well, and they wanted to rewrite it. The problem was, now if you're rewriting the whole code. You can't do that. It's too much of effort, and somebody else may beat you and so on. So their solution at that time was to make PHP better, and that's how the hip-hop virtual machine came into existence, right? Whereas if they had a microservice architecture, that was not a problem, because they can now convert part by part, and eventually and gradually migrate to a new system, whatever their new system would have been. So that's actually a big advantage, ease of migration. So there are different patterns for microservices deployment. You have the request response pattern on the right side. It's more of synchronous, and then you have the event-driven asynchronous. Typically in an application, you tend to use both. And in microservices, right, you don't have to follow one unique pattern of communication. You can choose certain patterns, certain services use request response, certain patterns use event-driven method for communication. Typically, how it works is you would divide your services in 3 categories. So tier 1, that's directly customer facing. Tier 2, that impacts the customer indirectly. And of course, tier 3, that has little or no impact to the customer. For example, let's say that for Jet, the front-end service is the tier 1. If it's down, you can't shop, period, right? That impacts you directly. Tier 2 is an order management system. So let's say you have placed an order and tier 2 service is down, it'll come back up later on, your order would get delayed. So you do have an impact, but it's not going to be a direct impact. I mean, your order might, instead of coming in 2 days, might come in 3 days. Sure, there's an impact. And an example of tier 3 is like monitoring service. If it's down, you as a customer don't know, you don't care, right? It doesn't impact you at all. Typically, tier 1 services generally tend to follow a request response pattern, and tier 2 and tier 3 would follow an event-driven. Why? Request response has a better error management. If your service is down, right, you get an error code back and you can take an appropriate action and you can notify the user because it impacts the customer directly. Whereas in event-driven, one big disadvantage is that when an event has happened, it goes like, an announcement is made. You don't know what happened. There is no traceability to that. So you don't want to put an event-driven service right in front of customer because, the customer places an order and then he doesn't know what happened. He should at least get an acknowledgement your order was received or something, or is being processed and so on. So that's typically the pattern we use. Tier 1 will go in the request response part. Tier 2, tier 3 would go in event-driven. Event-driven obviously has an advantage that it can scale better, right? You can add and subtract new services, whereas in request response, if you add a new service, you would have to change a lot of part of your code to accommodate that. So that is why request response is more rigid, whereas event-driven is a lot more scalable. So let's actually go into a little bit of a mathematical view of what a service is. And then it gets tied down to how functional languages would help that service. A web service is a function that essentially processes some input event and gives an output. And most of the services, especially in the domain layer, in the application layer, tend to be stateless. So in functional terminology, they are pure, right? They don't have any side effects. There is obviously a side effect for logging because you're constantly logging, but we don't really consider logging as a side effect in reality because it doesn't affect your system state, right? So side effect is something that changes the state of the system. Logging wouldn't do that. Then obviously you have the impure service, whereas let's say it's your service that reads and writes to your database, right? So if you have an event, write something, it changes the state of the system, in this case, the database. So there you can mathematically see that a service is a function that takes an input and state of the world and then outputs a response and another state of the world. In both cases, you are essentially, a service is a function. Now, before actually, and this is actually a pretty interesting part of it, before I go into functional languages, I'll actually do a little bit of a history of why we didn't use object-oriented programming. The answer is that object-oriented programming is dominant to a large part for historical and legacy reason. Now, if you look at the history of computers, right, early computers were based on Van Neumann architecture, somewhere around 1945. I believe the Mark I, EDVAC, EDSEC, they were made at Harvard and UPenn. And Van Neumann architecture simply is that you have a memory, which is your state, and you just manipulate that memory, right? So the early programming languages, C and Fortran and predecessor C, I think it was a language called B, and before B was BPCL. So C came from B came from BCPL. They both were essentially very low-level languages that closely manipulated the Van Neumann architecture. Because when you look at C, what you're really doing is you have these variables that you're making an assignment. What is a variable? A variable is an abstraction for memory. So when you're assigning and reassigning through all these loops and assignment statements, what you're really doing is you're changing from one state to another state. You're actually manipulating that state. So it gets directly tied down to the Van Neumann architecture. And as software grew more and more complex, right, you had the problem that it was hard to grasp, so object-oriented programming came into existence. And object-oriented programming essentially added two characteristics to a standard imperative domain. A, encapsulation. So you have the private and the public, right? You can control the state. And second thing was polymorphism. And that was achieved through the inheritance, right? So you can inherit a base class to a derived class and so on. And everything was great, except something really weird happened in 1990s. And what happened was that there was something called internet that came. And internet, as revolutionary it was, brought its own challenges. And the two key challenges that internet brought was the issue of portability and security. In a traditional mainframe systems, mini computers, even microcomputers of the time, you don't really, you install a software in your system and that's it. You just use it. You won't affect other people. Whereas in internet, now comes a problem that you have this application that's probably running somewhere else, and you don't know and you don't want to trust that application. So security becomes a huge concern now. And the second thing is portability. You go to google.com and you have a Mac or a Windows, and google.com server is probably running a Linux. Do you care about it? Do you know about it? No. The very definition of internet was that it was basically a kind of a technology agnostic method of communication. So portability became a key aspect. And that was where the languages like C++ failed. They allowed you pointers and memory manipulation, which should be forbidden, which is a big security problem, and they are not portable by definition, right? Every system you do Linux and you have Windows, you have a different set of API. So new class of languages came, starting with Java and more recently C#. And this was a key decision that they made, that if people are already used to object-oriented programming, so what we're going to do is we're going to target these new languages based on object-oriented paradigm, so it's easy for people to ramp up. So here's the thing. The only reason why these languages were based on object-oriented paradigm was because it was an established paradigm, so the developers can easily ramp up to it. It's not necessarily the best solution, it's the easiest solution. Why is it not the best solution? Well, when you look at these languages, they run on an intermediate layer called virtual machine, right? Java virtual machine or .NET runtime. These machines are not based on Van Neumann architecture, right? Object-oriented programming was developed to manipulate the Van Neumann architecture, but Java virtual machine doesn't run, like you run your code on a virtual machine, you don't run it on a Van Neumann. So you have this layer of abstraction in between, and there was absolutely no reason for you to just stick with object-oriented. You could have moved to somewhere else. The only reason why it was it just was easy for people to ramp up. And as a result of it, object-oriented programming just became the de facto. So, you can make an argument that object-oriented programming models an application as objects with states, but we just talked about microservices generally don't have states. And object-oriented programming, right, was designed for Van Neumann, whereas microservices run on virtual machines and real runtimes, which run on Van Neumann, of course, but you don't directly run your services on Van Neumann architecture. So this was actually a key unfortunate development. And when let's move to functional languages. And when you actually talk about functional languages, you would realize that the functional paradigm actually maps the services paradigm really well, because a service, physically a service is mathematically a function, right? And a service basically takes an event and outputs an event. And in FP world, you have algebraic data types, right? Scala, classes, and so on, that can model these events really well. And these events are immutable. A customer has placed an order at time t. That's it. That doesn't change. I mean, he can at time t plus 1 change that order or cancel that order, but that point of time, that event has happened. You can't go back in time and change it. So FP says, well, the events are immutable. And in services world, right, mostly you have stateless services. In functional programming, especially with Haskell, they have pure code. F#, Scala, they allow a little bit of impurity due to their compatibility with the runtimes. But mostly functional code is a stateless code, pure code. So functional programming captures this behavior of these service architectures very naturally. And they are often a very good paradigm to program web services. So we chose F#, which is actually a functional programming language for .NET. Typically, it is actually derived from OCaml, which was another language used for theorem proving. It was a derivative of ML that was invented, I think, somewhere in 70s. And it adds the object model of C# and .NET. And it's a statically typed managed functional language, statically typed because you have types declared, right? So when you compile it, if you have a type error, the compiler will point out. And it's managed because it doesn't run directly on the native hardware. You have the intermediate .NET runtime. And some of the key characteristics, obviously, it's more declarative in the style, in the sense that you tell what you want rather than giving a prescriptive style, which is you basically give a set of actions that need to be performed. Immutability in general, F# does allow mutability actually, but the language is designed in a way that it makes it hard for you to use mutability. So you can if you need to, but it'll just make it hard. So it prevents those unnecessary usage of mutability. One of the very common problems that people, when they move from C++ to functional languages, if you have a lot of mutability and impure constructs, they'll just abuse these constructs. So basically what they do is they just write an object-oriented code in a functional language, right? You see all the mutations and variables and so on. And at that point, why are you using functional language in the first place? So the language is designed to make it hard for you to use those impure constructs, but not impossible, because there are certain cases where you have to, right? Real world, unfortunately, has a state. You have your database, you have your network, they're all stateful. The infrastructure layer essentially is by definition quite stateful. And obviously you have higher order functions, so you can use these smaller functions and build upon them to create bigger functions. So there's some of the examples of F#. You have these types, these are basically ADTs, right? F# calls it discriminated union. And it's actually pretty easy to implement it, because how you define these services is you model it as a type for input, you model it as an output, and all you have to do is basically write a transformer that takes an input to an output, right? So in this case, you have the input type that I can search, an item name or item number, and you have an output that says, well, the item is in inventory, gives you a count, item is not in inventory, but it gives you a date, right? It possibly would be on this date, or we don't carry that item, right? And then you just can write a function catalog search that if user gives you a query, it searches and gives you an output back. And it also has all the constructs to do asynchronous programming. So this is an example of asynchronous workflow where you receive an order, user places an order, the system acknowledges, hey, I've received that order, and then asynchronously sends a message back to the order processing service and shipping service and so on, that would just package and ship it ultimately at some point of time. So one of the key things why I wanted to emphasize on static analysis is that because F sharp is pure, right, your output depends on your input in most of the cases. Techniques like static analysis are really effective, right? Because if you use a typical C++ and I call a method in a class or a function in a class, it might change the internal private variables in ways that I don't know. So it becomes hard for me to test, it becomes hard for me to reason the code, whereas in F sharp, it's actually very easy. Static analysis tends to be really easy, and we actually have static analyzer actually part of our build pipeline. So we define a set of NT patterns, and F sharp tooling it converts into an AST, and AST you can look at these patterns and so on, and we have different features like pre-commit testing, dashboard to track violations and so on. The static analysis tend to be a very effective technique for F sharp and in general for functional programming. Same thing, security, that was one of the challenge that we faced was choosing a non-standard language means there was a lack of third-party tools. So we built our own tools to identify the securities, identify the weaknesses in our application code. So finally, what are the benefits of F sharp? These are some of the main benefits that I thought we had: scalability, productivity, and code correctness. I'm going to get into details of each one of them. Scalability. Because you don't have state and state manipulation, right, you get inherent scalability because you don't have to deal with issues like mutexes and locks and all those things, right? If I give an input to a function and its output of the function just depends on the input, I can have as many replicas of the function as possible. It won't affect me. It won't affect my chain. It won't cause a bug. It won't cause any issues for me. So it allows you to scale, like from, in this way, 30,000 to 2.5 million without any issues. And that's a big advantage in the world of microservices, or in the world of web services in general, because most of your cloud providers provide you, in theory, an infinite resources, right? So you can be elastic, you can adjust your hardware usage based on your load. That's a huge advantage, scalability. You get just like the massive parallelism straight out of the box. Okay. Productivity. One of the key things is that functional languages tend to be really terse compared to an object-oriented. And part of the reason is that because you have higher order functions, you can actually abstract out the boilerplate code in those functions and recombine these functions in whatever way you do. So they are more concise and they are more, there's more clarity, you can reason more. And that's an advantage because the biggest cost to an organization is a programmer's salary, basically. So, and this is a common myth, actually. People say we don't use functional language because it's hard to find developers who are aware of it. Sure, but understand that one developer can actually do 3-4 developers' job because the amount of code he has to write is less. So if you need 100 developers of Java, you can probably get around with 20 developers Scala doing the same thing, right? So simpler code means reduced ramp-up time. If you have less code, you are onboarding new developers, it's easy for them to ramp up. And it's concise, less code means less chances of bug. So when you use a functional language, the compiler actually takes the onus and it does more work. So you're basically trading the work of a human and passing it off to the work of a compiler. Compilers tend to be much more sophisticated in a functional language as opposed to object-oriented. But yeah, CPU cycles are cheap. I don't care about that. As long as I save on the salary part, the developer cost, that's the important one. So I have some numbers here. They did actually, the study was done in UK. They had the same project done in C#, and they had the same project done in F#, and they have various statistics of it. But the key takeaway from this slide is that F# code tends to be 5 times smaller than C# code. That's the key takeaway of this slide. Another Uh, which number? 290 is comment lines. So you have these, useful lines in the sense that I won't call the blank lines as actually lines, right? And then you have null checks. I should actually probably mention that in a functional language, you don't have a concept of null, right? There's no null pointer. F# does it, but you have to add particular tags to it, but you replace it with options. So one of the big pet peeves in object-oriented is the null pointer exception gets eliminated. So that is why you don't really have null pointers. You do have some because you're interacting with C#, and C# has null. So at places you do have to have null. And then you have obviously the blank lines and the brace lines and so on. But as I said, the key takeaway is if you were to write 1,000 lines of code in C#, you can probably do the same in 200. Answers your question? Good. Okay, so let's actually go for code correctness. Because the language is statically typed, you are basically trading off runtime issues with compile time, right? So you have these algebraic data types, you have strict pattern matching, and so on. And what these algebraic data types do is they limit the number of possible states your system can be in. In fact, I'll digress, and I did a course. I was in Microsoft before JET, right? And I was doing a course on debugging, and they said the three top reasons why your application would crash is memory, memory, memory. What they're really saying is that if you think about memory as a state of the system, right, and you're using C# or C++, let's say you have 1,000 classes, hypothetically, and each classes have like 5, 6, some variables, private members. If you look at the number of possible permutation and combinations of all those, it's like huge. So like 5 to the power 1,000 or something. So when your system crashes, in reality, what happens is your system enters a state that it doesn't know how to transition out, right? And that's and because there's no exception handling, because you can't really, you can't really have exception handling for 5 to the power 1,000 states. It's too many states. It will crash. And that's what he's saying, memory, memory, memory. So basically, your system enters it into a state that it doesn't know how to deal with. And using algebraic data types, what you essentially do is you limit the number of states the system can. Because you can say, I have an order of an integer or something of a string and so on. You are putting these constraints in your types that you can't possibly exhaustively go into all of the states. And once you reduce the number of states exponentially in your functional code, you reduce the number of possibilities things can go wrong in equal proportion. And that is why functional code, if it compiles, because the compiler is going to do the type checking, if it compiles, is much more likely to be bug-free than actually an object-oriented code. Because essentially, the problem goes down to the state of the system. It's the state that's going to cause the problem. So you have strict typing. The compiler does all the type checking for you. It makes illegal states unrepresentable. You have exhausting pattern matching. So let's say you have a type X, and it can take one of the 5 patterns, and you account for 4. The compiler will say, hey, there's a 5th pattern that you did not account to. So you will catch that mistake right at compile time. And you also have immutability. So immutability means your variables will not be changed in ways where you didn't expect. So all this combination makes code correctness it makes your code, like if it compiles, it's probably going to be correct, right? It reduces the number of possible bugs in your system. So testing microservices, right? If you have a pure microservice, you can test exhaustively because there are no side effects, right? If you have one with state, then testing becomes hard. Same thing can be done for event-driven, except that you would introduce a test driver and a test interpreter in your message bus. One of the problems with microservices is traceability, right? How is the message flowing? So we have a platform, we call it X-ray platform. that actually traces that. We have a system called Pulse that does the SLA monitoring for system. Then we go into what is called as a chaos engineering. This is more from SRE discipline. The chaos engineering basically is a way in which you experiment a system, or you basically simulate a failure. So what chaos engineering in practice does is it shuts off some computer, it creates a chaos in the system. What if the data center goes down? What happens? How does my service recover? If it can recover, you know that you can handle a data center failure. And if it doesn't, you've identified a weakness that you can fix. So it's like doing live experiments on your system. And then obviously you have a distributed scheduler. We use Nomad, but there are a lot of schedulers like Mesosphere, and we use Nomad because we use a lot of other HashiCorp products. So it's very easy for us to integrate Nomad into a system. So conclusion. Very few startups have scaled to the size that we have. We got immense scalability and productivity due to our use of F#. We had an architecture which actually has not been changed since started, so it tells how robust it was. And finally, I'm up for questions. Yes, sir.
Yeah, I know you decided to use F# because you decided to go with Azure and the .NET platform. If you'd had another option available based on the JVM, would Scala or Clojure have done just as well?
Okay. So I'll repeat the question. The question was that we used F# because we had .NET platform. What if we want to use it for JVM? Would Scala or Clojure would have done as well? The answer is for Scala, yes. Some would argue Kotlin. Actually, Kotlin has a problem that it's not exactly functional. Kotlin has an advantage that it's more lightweight. Scala tends to be more heavy. That's why for Android application development, Kotlin is actually a very viable choice. People don't use Scala, but Scala would work perfectly well. Clojure, I am personally not a big fan of it because I do love my static typing, and Clojure does not have that. So if you're going for a test code where your test is like 15 lines of code, probably Clojure would do, but I would avoid using Clojure for a large system. Yes?
How did you define your interfaces between microservices, and how did you evolve those over time?
So the question was, how did we define the interfaces between microservices and how did we evolve in time? Now, we usually, F# has a feature, it's called type providers actually. So what it does is you provide a sample and it defines a type based on that sample. But you actually can model it. There are several ways you can attack this problem. You have Google protocol buffers, right? So you can basically define your interface as a protocol buffer file and then derive objects that can read and write. We particularly actually use just plain old JSON, which is not the best and most efficient, but it just works for us because our message size tend to be small. But depending on your own application, you could have JSON, you can have protocol buffers. Now, the second part of it is how would you evolve over time? That's actually a little bit tricky. Generally, when you evolve a message, you have what is called as a tolerant reader in the sense that you add fields, but you don't remove fields for backward compatibility. So that way, the code that is already writing in an old format, it works. Now, if you do need to remove, that actually gets a little bit tricky. There are two ways you can do that again. A, you can always attach all the data types with versioning. So you know that you're using an old version, you know you're using a new version, and then you can phase out the old version. Another thing that we are actually moving to is we are moving to monorepo. So where all the services, monorepo actually works really well in microservices context. You actually, you have all your services as one repo. So if you change the contract, basically the build will break until you fix it. So that way, you solve the evolution problem in the sense that if you have to make a change, you basically make a change everywhere where the contract gets used.
Would you have to roll them all out at the same time?
Unfortunately, with the monorepo, yes. More questions?
Can you tell us a bit more about this using a monolith? How are you doing it?
I have time or? Okay, we can talk offline, right? I had the clock in front of me, it was 0, so that's fine. Okay, thank you.